The Honda Civic has a lot going for it. It is very sleek at the back, and there aren't any major flow control devices sticking up into the air to create drag. So it should have a low drag coefficient. But it doesn't. In the simulation at 80 miles per hour, its drag coefficient is 0.3, which isn't bad if you compare it to the average car. But this is a sedan, with a very sleek rear and small rear face. Hatchbacks like the Peugeot 208, which we looked at here, have drag coefficients well below the Civic and with much larger rear faces. The reason why that's so impressive is for cars, the rear face is the biggest problem for drag. Because it is so large and exposed to low pressure, a lot of drag is produced by it. We'll get into that a little more later. But here, the Civic has a very small rear face. The designers did a very good job shrinking it after the rear window, but still the Civic gets a drag coefficient similar or worse to cars that it shouldn't be really similar to or worse than. What's more, while producing such a high drag coefficient, it also produces a lot of lift. At 80 miles per hour, it produces 23 kilos of it, which is very easy to see why. It's effectively a wing. We'll cover that idea more later on too, but just a quick explanation of it. So the underneath is flat and the top is curved, so it acts like a wing. A wing produces lift, so this car produces a lot of lift too. The fact that it approximates a wing makes its drag coefficient even more surprising because wings have low drag coefficients to begin with. So how does this car produce such a high drag coefficient despite having so many things going for it? That's what we're covering in this video today. Also, we were asked by a client to make this video very detailed and long, so this video will go into the details much more than our other videos. To begin with, the flow is 80 miles per hour or 35.76 meters per second. That's an important number because it directly impacts how much energy the flow has. At the start, the flow has the most energy it will ever have. From here, anything that it touches will take away some of its energy. That's not to say that there won't be regions where local flow has more energy, but overall the flow will reduce in general. So whenever there is a region with more energy, there will then be another region with less energy and it will cancel out with that higher energy. A way of measuring the energy of the flow is the dynamic pressure. It's equal to half times the density times the velocity squared. We cover in more detail in this video Aero Fundamentals number 6, static pressure, dynamic pressure, and total pressure explained. The dynamic pressure is effectively the kinetic energy per unit volume of the flow. It is calculated by the equation half times the density times the velocity squared. In this flow, the free stream dynamic pressure is 767 pascals. Now this number can be a little misleading because while the total energy of the flow cannot increase past what it initially was, and it will actually drop, the dynamic pressure in particular can go above the free stream dynamic pressure. It does that by converting some of the static pressure into dynamic pressure. Static pressure is the pressure we feel in the flow as we move with it. Dynamic pressure is the additional pressure we would feel if we were to stand still and let it hit us as it decelerates. In this sense, the static pressure is like the potential energy of the flow, while the dynamic pressure is like the kinetic energy of the flow. Each can be converted into the other. Why is that important here? Well, the very first aerodynamic thing we see on the car is a real example of this process. At the very front of the car, you can see how the flow coming in is at some velocity. Initially, the free stream flow speed of 35.76 meters per second, but as it reaches the car, it turns bluer and bluer. It decelerates. Here we're looking at around 5 meters per second perhaps. Right there, we can conclude the dynamic pressure, so the kinetic energy of the flow at this point has dropped. Calculating the dynamic pressure by using the equation half times the density times velocity squared, we're now looking at around 3 pascals. The dynamic pressure dropped then from 767 pascals in the free stream flow to just 3 pascals now. Almost all of that flow's kinetic energy is gone. Where did it go? There are 2 main places. The first is the static pressure. So if we look at this plot, which is the exact same one but now colored in the static pressure, not the dynamic pressure but the static one, as the flow approaches the car, the static pressure increases, it becomes redder. So some of this dynamic pressure has transformed into static pressure. But if we look at the general numbers, there's something missing. So the dynamic pressure in the free stream flow was 767 pascals. If the transfer from dynamic pressure to the static pressure were 100% efficient, the static pressure should raise by 764 pascals. Note that the color bar is in gauge static pressure. This is the static pressure reference to the static pressure in the free stream flow. So a positive value means the static pressure increases by that much relative to the free stream flow. And in front of the car, we definitely do see a positive value. But it's only around 600 to 650 pascals, not 764 pascals that we might get if we were to transfer all that energy between kinetic energy to potential energy. So immediately, this flow, the very first flow hitting the car, is losing energy. Now we have less energy to work with, but it's even worse than that. We also have high pressure at the front of the car. Remember earlier in the video where I said how low pressure on the rear face and the rear face's size really affects the drag coefficient of the car? Well, now we're seeing the other half of the story. So the truth is that the low pressure on the rear of the car doesn't actually matter, nor does the high pressure on the front of the car. What actually matters is the pressure difference between the two. If the pressure at the front is the same as the back, then they cancel out and you get no net force backwards. That means you don't get any drag. But for every car out there, the pressure at the front of the car is always greater than the pressure at the back. That means that there's always a pressure difference. That creates a force backwards, drag. As such, the drag coefficient increases. There are a couple of ways to reduce this drag. The first is to lower the pressure difference between the front and rear. The second is to reduce the size of the faces of the front and rear. By doing that, you reduce how much surface area is exposed to these undesirable pressures, hence the drag drops. This top view shows the situation even better because we can see just how much the front is exposed to this really high pressure flow. One thing to note is that this really high pressure, this red area, is only concentrated to the very front. Once we head to the edges, it drops. What is going on here? Well, the front experiences such high pressure partly because it's so flat, and partly because the flow here has all the energy of the free stream flow, so it can convert that into static pressure. As we head to the edges, the car's front is round, so the flow hitting it doesn't hit it straight on, but at an angle, so it doesn't decelerate as much. You can see how the flow speed is still around 30 meters per second. But there's another reason the flow around the edges has a low static pressure. That's because it is also mixing with some faster flow. So these regions are regions where two general flow streams are meeting. The flow from upstream and the flow from around the front of the car. The flow from around the front of the car has to go somewhere. It isn't completely stationary yet and still has some speed. It can't go forwards because there's a flat face blocking it. And even with the radiated flow, there's too much air in the way, so we see a lot of flow in the front has to be diverted around the front. Some goes over, some goes underneath, as we'll cover later, and some goes around the sides. So we have this slower flow coming around the sides and meeting up with the fast moving free stream flow. The free stream flow bends out a little, but still, there is some joining going on. As a result, the flow around the edges of the car is naturally slower. It's some combination of the regular free stream flow and the slower flow coming from the front. Because it is initially slower, it has lower dynamic pressure, so when it hits something, even if it's brought to complete rest, the static pressure it produces will still be lower. So here we have lower static pressure because the flow isn't slowed as much, and because it was slower to begin with. There's still a little more to cover about the edge flow though, but we'll cover that next. Let's go back to the front and rear pressures and finish off that bit. Here, Honda has done a great job reducing the rear face's size. That makes it even stranger why it has such a high drag coefficient. So the front of the Civic is not really any better or worse than an average car sedan. The pressure is very high here and the face is quite large. So half of the equation is bad here, the front is bad, the rear not so much. As such, from the front we can understand why there is a little more drag than there should be, but still, there must be other areas letting the overall design down. Just quickly, if you'd like us to simulate your very own car, let us know here. Let's come back now to the edges. Looking from above, the static pressure is actually negative. It's blue at the very edge of the front. Why? This is because of something called Bernoulli's equation. So looking at the velocity, it gets really red, the flow speeds up a lot as it races around the edges. Bernoulli's equation states that with all else equal, if the velocity increases, the pressure must drop. Because the velocity increases here, and a lot, remember that this flow was a little slower than the free stream flow to begin with, and because it was combined with the free stream flow and the slow flow from the front, it is accelerated a lot by now. Now one question that arises is, why did we get flow acceleration to begin with? So that question is actually one of the most controversial questions in all of aerodynamics. It actually ties directly into how a wing produces lift. The reason why a wing produces lift is still up for debate, however, in my opinion, is because of the Venturi effect. And if you're a hardcore aerodynamicist listening to this, there's a good chance that you're frothing at the mouth because of the idea that we're getting lift because of the Venturi effect. You might be a supporter of one of the other couple of leading theories, but let me explain. So the Venturi effect is when you have a contraction in a pipe. The flow entering has to speed up to get through. This is just a function of mass conservation and incompressible flow. We actually cover the Venturi effect and Bernoulli's equation in the video here in more detail. Now, I said that this is what happens in a pipe. That is actually a key detail because a pipe is closed around the sides, so none of the flow can escape elsewhere. It has to either go front or rear, and it can't go backwards because there's more flow. It can't go left, right, up or down. So as such, it only goes forwards. Here we don't have a pipe, we have a car, and the same applies to a wing. We only have one side to the pipe effectively, just the side of the car. There's no other side, it's just free space down here, so the flow blows out and isn't restricted by any other wall. But it actually is restricted to some extent. It's restricted by viscosity. Viscosity is the arrestive force. It does everything it can to stop motion between different parts of flow. Here, the flow cannot blow out as much as it likes because viscosity is resisting the outwards motion. So the problem of having so much more air to flow around the car is solved partly by blowing out and partly by the flow accelerating. We can actually see this problem being solved in the pressure plot too. So close to the car, the pressure is lower than far away. That right there shows how far away the pressure is pushing the flow closer to the car. That shows how the flow around the car's edges can't blow out as much as it would like. It has that higher pressure pushing it in. So you can see the same thing on a wing where the further away you go from the surface, the less the streamlines are curved and the less the pressure changes too. And I know I'll get a lot of resistance on this idea that the Venturi effect coupled with viscosity is the reason why lift is produced. And I'm not the first person to think that. Actually, a little while back, I woke up early in the morning with this idea. I don't know why I get these ideas. My dreams must be different to everyone else's. I think that I have all my perverted ideas during the day, which leaves my dreams for the serious work. But anyway, if you look at the pressure changes over a wing's surface and over a car's edge here too, the pressure changes in a consistent way to how it should with the Venturi effect. So all the pieces of the puzzle align with the Venturi effect and viscosity explanation. And I know that we're talking about cars here and I'm over here talking about wings, but in this particular respect, they're actually fundamentally the same. They're just a curved surface with a lot of air that has to flow over it somehow. That's why I think the pressure is dropping around the edge. Let's now move to the underbody of the car, the front lip, because we see something Honda has done really well here. The flow underneath the front lip is pretty much attached. It's a little slower, but I can't see any flow separation. Maybe there's a tiny bit, but even still that's way better than a regular car. Most cars have flow separating over the lip and that increases the drag. Here, Honda managed to keep the flow attached by increasing the front spoiler/splitter. To explain why, we need to look at the flow around the front. We've already covered as the flow hits the front of the car, it has to go somewhere. Some went around the sides, and here some is going down. Look at just how curved the flow is here. But the splitter extends out and cuts into less curved flow. The flow that's hitting the splitter is significantly straighter, not completely straight, but definitely not 90 degrees like we have closer to the car. That straighter flow can now go underneath the sharp lip of the car and stay attached. So instead of having a shorter splitter and trying to get near vertical flow to travel around a 90-degree edge, with a longer splitter, there's now maybe a 50-degree flow traveling around the sharp edge. Now that's a very interesting point. A 50-degree angle is still huge. The flow should still separate around the splitter's edge, but it doesn't, or at least almost not. Again, it's very difficult to see a tiny amount of flow separation. So how does the flow stay attached, at least mostly, around this 50-degree edge effectively? It's pretty much because you have so much flow being crammed underneath that it pushes the flow up to the surface of the car. And that's maybe what we're seeing with just after the lip. The flow is curving downwards to separate, or just having separated, but then the flow underneath the car pushes back up and makes it reattach. The pressure plot supports this idea because underneath the lip, there's good low pressure, which is good downforce, but then there is this higher pressure flow pushing back up. The low pressure comes about because the expansion of the flow around the edge. It slows down. But the air being crammed underneath is high pressure, and high pressure always pushes low pressure around. Now in this plane, we can also see what the flow over the hood is doing. In one way, Honda has done a very good job here, in another way, not so much. The good way is that the flow stays attached very nicely. There's not even a tiny indication that the flow wants to separate over it. As such, the drag is lowered. There's still a little bit of drag, but that's for the grille, not for the hood. Honda achieves this by really curving the front of the hood. It's so curved that it's effectively in line with the angle of the flow coming in from the front. That's really hard to do. I imagine Honda curved the front so much for this exact reason. While this is very good from a drag point of view, it's pretty bad for downforce. In this pressure plot, we can see just how much low pressure is formed over the nose. If we compare the low pressure zone over the front of the hood to the low pressure zone underneath it, it looks like in this isolated region, lift is produced. That's because the pressure over the front of the hood is lower and it covers a larger area. So more lift is produced in two ways here. The reason why we get such low pressure over the front of the hood can be seen in the velocity plot. The flow accelerates 20 or 30%, and from Bernoulli's equation, and because the height changes almost nothing, that has to come with a drop in pressure. So this region is fairly straightforward, and the way to increase the pressure here would be to reduce how much the hood is curved at the front. I think that is definitely doable without increasing the drag because the flow looks like it's in good condition already. It has plenty of kinetic energy to stay attached, and the angle the hood would make with less curvature would still be fine. Just quickly, this simulation was done with OpenFOAM. If you're interested in learning OpenFOAM, then check out our courses here on Special. Let's now move further up the hood. The hood isn't really sloped too much. Because of that, we can see the flow having to redirect over the windshield quite a lot. It has to do that because the windshield is definitely not even close to being in line with the hood. This is often done for aesthetic purposes. If you slant the windshield down more so the hood is more in line with it, it gives the car a more sporty and even aggressive look. At the end of the day, a car's looks is the main selling factor, so while slanting the windshield up and not sloping the hood up as much is bad for aerodynamics, it was done for styling purposes. We know it is bad for aerodynamics, but why exactly? Well, the reason is quite intuitive. Because the flow has to divert so much, like we saw at the front of the car, the flow will dump some of its kinetic energy into the windshield, slow down, as you can see here, and transform some of its kinetic energy into static pressure. We see that in the pressure plot, where we do get high pressure, red coloring around the junction of the hood and the windshield. It's not as red as the front, and that's because the flow here isn't decelerating nearly as much. The flow here only has to divert around 30 degrees, the flow at the front has to divert like 90 degrees. From this angle, it's a little hard to tell just how much the flow is being decelerated, so let's look from on top. We see here something really surprising. Look at the extent of the flow deceleration region. I mean, the windshield is curved quite a bit, but even at the edges of it, we still get much slower flow. With that comes high pressure across the window. That high pressure is good in that it pushes the car into the road, but we can see how the windshield is angled. That is an important point because pressure can only ever really act normal to a surface. Because of this angle, the force created is now partly in the vertical direction and partly in the horizontal direction. So we get more downforce out of it, but we also get more drag because the pressure at the front pushing back is much higher than the pressure behind the car. Slanting the windshield will come with low pressure, which will reduce the drag, but the drag will also reduce more because if the windshield is slanted more, the force created by the pressure will be more upwards. So there will be two reasons for the drag reduction. Now looking at the roof, we get major flow acceleration, the fastest flow we see anywhere on the car. That's even more impressive considering that the flow entering the roof section is a flow that has already lost so much energy from the front and windshield hood junction. Yet it still reaches almost 50 meters per second, 40% more than the free stream flow. The same thing happens here as over the front of the hood and the edges of the car. The acceleration comes with very low pressure, and the lowest pressure we see out of anywhere in this plane. That's not a coincidence because if we have the greatest acceleration anywhere in this plane, then that will probably come with the lowest pressure too. This is a problem that many cars have, and the more bubbly the car is, the worse this problem is. For example, in this video, we go through the aerodynamics of a Tesla and how to fix this exact problem with an out-of-the-box solution. To understand why we get this problem on so many cars, let's revisit the idea that this car is effectively just a wing. It's also cambered, so the top is more curved than the bottom. That makes it naturally produce lift. That's exactly what we get here from the roof. Because the roof is so large, we end up getting a lot of lift, and this region is a major reason why this car produces 23 kilos of lift. In fact, it's not really that hard to tell if a car will probably produce lift. One key indicator is just how sleek it looks. The more wing-like it looks, like here and the Tesla Model S, the more it will produce lift. The only way around that is to have a very aggressive diffuser and underbody setup. Using other flow control devices, a huge rear wing, will come with a too high a drag penalty given just how large it will need to be to overcome the inherent lift producing design. So if this design is so bad from a lift point of view, why is it so common? The main reason is because you need to put people somewhere. Currently self-driving cars are not here, so people can't go on the boot yet. But this design is so commonly used because it is a very easy way to reduce the drag coefficient of a car. Because the rear is sloped down so much, the rear face becomes very small. That means that even if you get low pressure there isn't much surface area for it to work over, so the resulting force is very small. You get a small wake too, and that all adds up to low drag. And while it's a very intuitive approach, for the last 10 years or so, it has always amused me because about 10 years ago, there was a kind of a big push in the automotive industry to reduce the CO2 emissions by a certain amount, and the goal was by 2020. I don't actually remember what the name of it was because whenever we had meetings and seminars about it, I was struggling to remain conscious. Anyway, because I came into the industry a little after the ball had already started rolling, I kind of saw it with fresh eyes, and it was hilarious because there were so many manufacturers putting in so many resources to making their car lower drag and coming up with elaborate designs, and then Mercedes just decided to shrink the rear of the car and get almost the required goal in one fell swoop. Just by stepping back and thinking about it, they came up with a very elegant design, yet simple, to a problem that most manufacturers were and still are struggling with. Moving to the rear window, we see a really good part of this car, something that many other cars could use. Look at how little the pressure changes as you move down the window and even over the boot. That might not seem like much, but because the pressure stays almost constant, the boundary layer over the rear is much thinner than regular cars. Just a quick explanation of what the boundary layer is, it's the air closest to the surface. Here you can see that as we approach the surface, the flow becomes greener and then even blue. In fact, this region is so thin on this car that it's hard to see. But this boundary layer is part of the flow that meshes with the car's surface. In fact, all objects where the flow is attached have one. The reason why this is so small is because the pressure over the back doesn't change much. Because this flow is slow moving and any high pressure downstream of it will push back on it, it will then decelerate it further, and that makes this layer thicker. That in itself isn't a big deal, but it becomes a big deal when you have something downstream of the car that you're trying to use the flow with. For example, putting a rear wing on a car is not as simple as it might seem. The major problem is mounting it too low. If you do that, the rear wing will see slower moving flow and it will produce less downforce. When you consider the equation of a downforce, and that is proportional to the velocity squared, even a slight reduction in the flow's velocity hitting the wing will come with a much larger reduction in the downforce. So to mount the wing, you should move it above the boundary layer. That can be a major problem for some cars where very thick boundary layers form. But for a car like this, it's a lot easier. You can mount it closer to the surface and still get faster moving flow. Here, and like every car, you want to mount it in the free stream flow. For this car, it's about here. Now for rear wings, we talked about how much this boundary layer will negatively affect its downforce production because of the reduced velocity over it, but it can also reduce its downforce another way. So the slower the flow is over a wing, the more likely it will be to separate. That's because a wing has an adverse pressure gradient too. That pushes back on the flow, and if there's too much, the flow will separate over it. We know now that the Civic has a small boundary layer, and why that's a good thing, but why does it have a small boundary layer to begin with while other cars don't? It has a lot to do with the rear of the boot being flat. Often manufacturers will put a little spoiler or even a lip at the end. Believe it or not, but something that small greatly changes the pressure upstream. If you'd like to see an example of that, check out a video we did on the BMW M2 in the description. Having anything disturbing the flow downstream will create a back pressure upstream and thicken the boundary layer. But on the Civic, we do get a small region of high pressure. It's not much, but it's there. That's where the window meets the boot. And actually, that very small bump shows just how sensitive this area is to disturbances and how high pressure can be created very easily. Now, like the windshield, the pressure over the rear window and boot has a more complicated effect than just increasing the drag or increasing the downforce. Because this surface is sloped, so that it's something between vertical and horizontal, the resulting force from the pressure will be somewhere between the lift direction and the drag direction. As such, this pressure contributes to both. But unlike the windshield where high pressure is good for downforce but bad for drag, here high pressure is good for both downforce and drag. It's obviously good for downforce because it pushes the car down into the road, but it's good for drag because if you have high pressure on this face, it pushes the car forwards, and you can counteract some of that high pressure you have at the front pushing the car back. But while having high pressure here is good, the key is to do it without increasing the drag elsewhere. For example, the rear spoiler is great for increasing the pressure over the rear window and boot, but that also comes with an increased wake size and increased drag. The net result is then an increased drag. Let's now move to underneath the car to the diffuser. Here we actually see one region that is letting the car down big time. Remember that this has a drag coefficient of 0.3, which is pretty average, but a lot worse than this car should have given that its general design is very good and has a small rear face. The diffuser is one reason why the drag coefficient is so high. It's not done well. Let's cover why. So the diffuser is the rear bit of the car underneath. Its role is to create low pressure underneath the car at the rear and hence downforce, but it's also one of the few features on the car where both downforce and drag reduction can occur simultaneously. Usually when you produce one, you produce the other. Here though, it reduces the drag by shooting the flow up and reducing the wake size. It can be too aggressive and shoot the flow up so much that the wake increases and hence the drag increases, but for most cars, that's not the case. For this Civic, we can see just how gentle the diffuser is. It's almost non-existent with almost no sloping up at all. That is reflected in the wake where the bottom of the wake isn't really shot up. It's more just limping along horizontally. That is a dead giveaway that not much downforce is really being produced here by the diffuser. We also get an indication from the pressure plot. The pressure isn't that low, and we even get little regions of high pressure too. That's not great for downforce. Now looking at how much the flow over the boot is shot down, we can go even further and say that this region is actually producing lift. That's because the diffuser just isn't sloped very much, so it can't override the downwards direction of the flow that the top of the car is producing. And because it isn't sloped very much, the wake is much larger in the rear than it could be. This drag orbit shows just how much drag is produced at the rear. Really, Honda didn't do too much with the diffuser here. They might have chosen this approach to increase boot space, or maybe they just didn't want to put resources into designing the diffuser. I don't know. Either way, there's a lot of potential to improve the car's aerodynamics with a good diffuser here. Even a moderately good diffuser could drop the drag coefficient by like 10 or 20 counts and reduce the lift too. But despite this major flaw in the diffuser, which increases the drag a lot, the wake is still impressively small, smaller than regular cars, so imagine how much smaller it would be with a good diffuser. What we have seen so far has mostly been in the center plane. Let's shift over half a meter to the left where we see a bunch of new flow features and some flow features are changing, but some are the same. For example, the hood, front and roof, but others like underneath the car, we do see some differences. We see high pressure here now. That's really bad for downforce. The splitter is still working about the same way as it was when we were in the center plane, and the flow still stays attached over it. In fact, I'd say it's in better shape here. It's faster, but there's less low pressure now and even high pressure. The high pressure occurs for a similar reason as the high pressure we saw under the center plane, but there is an even more extreme case here. We have quite a lot of back pressure forming, pushing the flow back. This is effectively because there is much more air trying to cram through a small space, and in this plane, we also have the wheel affecting the flow more. That's kind of like an additional wall corralling the flow. Now behind each wheel, we have large wakes. These are coming from the wheels. We not only have wakes from the back of the wheels because as the flow wraps around it, it separates, but we also get wakes from various vortex structures forming around the wheels. The most notable is the journey vortex. So as the flow hits the front of the wheel, it has to divert again up, down, left or right. The flow that goes down hits the road, and because it can't go downwards anymore or forwards or backwards or up, it has no choice but to go left and right. As it flows around the edges, it rolls up into a vortex commonly called a jetting vortex. In this plane, we're not actually slicing through the wheels yet, but we're still seeing their wakes. Much of these wakes are those jetting vortices that are spewing out the sides of the wheels. That definitely increases the drag of the wheels, and we can see in this drag orbit just how much drag is produced from them. In fact, this shows us one of the reasons why the Civic has way more drag than it should. The wheels are very bad. The wake behind the rear wheels is especially bad. Looking at the boot, we see a much thicker boundary layer forming here than we did in the center plane. The pressure shows us why it's so much thicker. As you go down the rear window and along the boot, the pressure increases. It goes from very blue to just light blue. That is now an adverse pressure gradient we talked at length about earlier. Because it's pushing back on the flow decelerates and the boundary layer now grows. Let's now move to looking down. We're half a meter off the ground and the sides are very impressive. There's almost no wake. The flow stays attached and is as straight as an arrow. This is very different to some other cars. Often what happens is the flow inside the wheelhouses blow out the top and creates wakes along the car's sides. We've seen that in other videos that we've done, and usually they're the cars where the wheels don't take up much of the wheelhouses. That leaves a lot of room for the flow to come out of the top of the wheelhouses. Here, the wheels occupy most of the wheelhouses, which is good for drag overall, and we see one of the major benefits to it. There is almost no wake from the top of the wheels. Those wakes are isolated to more the lower half of the wheels. The only somewhat bad part around the sides is the rear edge, and again, it's not even that bad. It's better than a lot of cars, but you can see where the flow separates here. Given how curved the surface is, there is potential to make the flow wrap around a little more. That will reduce the wake size and increase the pressure on the edges of the rear car, and that would then reduce the drag coefficient. Again, it is very good how it is, but this is one minor improvement that could be made. Moving up 1 meter off the ground, we can see something really cool. At the rear of the car, you can see these two greenish streaks, one for each side of the car. They actually come from the C-pillars, which are what the rear edges are called. Given how they kind of tumble around, we get some indication that vortices are produced, but it's a little unclear. If we look at the streamlines, we now see a little more that the streamlines aren't quite a vortex, but they're rolling up a little. The reason why this is cool is because these are effectively wingtip vortices. A wingtip vortex forms when you produce lift on a wing, so you get low pressure on one side and high pressure on the other. So the flow wraps around the edge and rolls up into a vortex. You only get that when you produce lift or downforce. Here, the car is very wing-like, and it naturally produces lift, so we naturally get these vortices, even if they are very weak. So the car is acting like a wing, which makes its high drag coefficient even more surprising. Another thing that makes these vortices cool is that usually we get vortices when the C-pillars are much more upright. Here they are sloped so much, which adds to the wing shape. So we still get vortices here, but for a very different reason. These vortices are still bad for drag because they are wasted energy, and actually, they might be one of the reasons why we get a thicker boundary layer in the off-center Y plane. They might have been washing up the flow here, which naturally increases the boundary layer thickness. The side mirror wakes are pretty good, not great because they're quite large, but good in that they flow into the car. That reduces the wake and drag. So that brings us to the end of this long video. I hope you enjoyed it with all these details explained in depth. If you'd like us to simulate your very own car, let us know in the link in the description below. If you're staying on YouTube, YouTube thinks you'll like this video, so check it out. Thank you very much for watching. Peace out, amigos.